Hello everybody, I am Marouane Tliba, a master student from the National Institute of Telecommunications and ICT around Algeria. It's my great honor to present you today our work 2D-based Saliency Prediction framework for omnidirectional 360 video. This paper is in collaboration with Dr. Mohamed Sayah from Oran University, Algeria, and Yasser Dahou from Dublin City University, Ireland. As a brief outline, my presentation will be divided into the following part. Starting with problem setting, then defining the dataset in which we have made our experiment, then describing in detail the proposed framework for head and eye movement prediction, then discussing the qualitative and the quantitative result of our framework, and finally the conclusion. The idea behind saliency prediction is that we want to be confident where a human would look toward a given scene. Saliency prediction is the task of modeling human attention computationally, and the goal from it is to build a function f with some parameter theta in order to produce a heat map probability called a saliency map from an input image x as illustrated below. Saliency map is a multimodal Gaussian probability distribution where each probability refers to how likely the corresponding input pixel from the image X tend to be salient or attractive to human attention. 360 video frame represented under a new kind of multimedia content called spherical or omnidirectional. This is images frame cover the whole spherical view in space, 360 degree times 180 degree, where the user had the freedom of attending to any direction just by moving his head around the 3D space axis, X, Y, and Z, so that at each time step, a human attend just to a specific position in a small portion of the entire sphere, which represent the rendered viewport. So the main objective from saliency prediction in 360 video is to predict the most probable viewport in a frame reflecting the average person head movement, but also the eye movement reflecting the region of interest inside the predicted viewport. And hence, we have two types of saliency in 360 video, head movement prediction and head plus eye movement prediction. And of course, there is a couple application of saliency prediction, especially in 360 video, because immersive experience is supported by a frame content with a very high resolution, from 6K to 8K. The transmission of omnidirectional video usually consume 4 to 6 times of the bandwidth of a regular video with the same viewable resolution, which means a huge challenge to traditional video streaming architecture. The more amount of data is the major challenge that omnidirectional live streaming system need to address. So by head and eye movement, those systems would be able to predict the viewed region beforehand during live streaming. We have applied our experiment on Salient 360 training dataset, which has been proposed as a part of Salient 360 Grand Challenge that contain about 20 videos with diverse characteristics from the number of fixation, frame rate, indoor or outdoor scene, and with a fixed camera or traveling camera. Each video labeled both head movement saliency and head plus eye movement saliency. The plot below represents the correlation between the head-only maps and head plus eye maps, and they are not much correlated with a CC less than 0.5. Despite the remarkable improvement in 2D saliency modeling with recent state-of-the-art model, the advancement of 360 saliency is still very much limited. In order to adapt the 2D saliency model on 360 frame, we need first to project this omnidirectional frame to a planar format. So that we need to apply a sphere-to-plane mapping. The most known and common kind of projection and sphere-to-plane mapping with a uniform quality are equirectangular projection and cubemap projection. Both of these methods allow us to have a 2D plane images, but unfortunately introduce some problem during the feature extraction. For the equirectangular map, the sphere is projected in one map, but result in adding some redundancies as we go toward the poles. So the planar CNN won't be able to extract feature pattern in this region, which result in the impossibility of predicting saliency as well. For the cube map, the sphere is projected to an independent patches, where each patch or cube face processed alike, and of course that make laws of the global content characteristic of 360 frame and make laws to the global attention. So each projection format introduces specific aspect of benefit, but at the same time suffer from some drawbacks. Most of previous work use one kind of projection, focusing just on a specific part of modeling attention in 360, either the global attention or the local attention. In this work, we are trying to leverage the power of 2D saliency model in predicting head and eye movement in 360 video without requiring any depth adaptation of the predicting algorithm. Alright, this figure depicts our framework, which is consisted of two streams. One uses the ERP or equirectangular projection, and the other uses CMP or cubemap projection. The same 2D saliency model is placed within the two streams to predict an equirectangular saliency map from the first stream, and 6 saliency map or 6 cube faces from the second stream. After that, we apply an inverse projection to these cube faces or these 6 saliency patches in order to transform it to an equirectangular saliency map as the form of the first stream. Each stream saliency map covers a specific aspect. The first stream saliency map is precise on the equator and underestimate the saliency on poles. The second stream saliency map is more rich than the first stream, where it's kept saliency well around the equator but overestimated on poles because of the artifact distortion introduced by the inverse projection. Considering both equirectangular saliency map as a series of probability distribution, we have applied pixel-wise joint probability distribution formula consisted of 3 terms: the merge term, the noise term, and the bias term. The merge term take advantage of the normalized information from the distribution by leveraging more the rich information than the precise information in the equirectangular saliency stream. The noise term maximizes the material and the common information using element-wise head-marked product for the intersection between the two normalized distributions. We consider that it is useful to incorporate a bias term in the equation in order to shift the probability origin based on the saliency longitude location on the sphere, where B is the complement of the equator bias We have set the parameter after an extensive experiment. We set alpha to 0.2 and beta to 0.4. And finally, after adding the adaptive equator bias, we got the 360 saliency corresponding to the viewer head and eye movement position. The framework is built on top of 5 different 2D state-of-the-art saliency models: ACLNet, Salima, TZNet, Critisal, and Salicon, to address the saliency prediction in equirectangular video, but any other saliency model could be used. The model leverages different properties for feature computation. ACLNet and Salicon use an attention mechanism and a two-stream, respectively, for a robust global attention modeling. 3D SAL and TZNet use a 3D convolutional for spatio-temporal feature extraction, while Salima's main contribution is a conceptually simple exponential moving average of the internal convolutional state. This table shows a comparative study of the selected model according to the 3 options: ERP, CMP, and framework, using 5 common saliency metrics. In the first option, we compare the output of ERP stream with the ground truth. In the second option, we compare the output of CMP with the ground truth. And in the third option, we compare the output of the whole framework with the ground truth. It is clear that the proposed framework for 2D saliency model gives the best result compared to the direct prediction on equirectangular and cubemap feature. This table shows the comparison of our 2D based saliency model framework against 360 saliency state-of-the-art model, CP360 and Wuhan University model, which is the state-of-the-art model published on Salient 360 benchmark. We could remark that our proposed margin probability distribution framework using the different 2D saliency model is very relevant and competitive with 360 saliency state-of-the-art models, where we could remark that ACLNet achieved the best NSS and CC, but also TZNet achieved the best SIM and KLD. It can be observed that the proposed margin probability distribution framework using the 5 model is able to handle various challenges seen well and produce consistent omnidirectional video saliency result. Also, we could notice that the result of some 2D model using the proposed framework as TZNet and Salima are more comprehensive than other models and look remarkably similar to the ground truth map in terms of saliency distribution. So, in this work, we are proposing a novel framework that allows the application of existing 2D saliency model designed for 2D dynamic and static scene on omnidirectional equirectangular video frame, adopting a weighted joint probability distribution. The proposed framework, without any depth adaptation of the prediction algorithm or training or fine-tuning on 360 saliency dataset, have demonstrated to be competitive with state-of-the-art head and eye saliency model. We also think that the resulting improvement of our 360 saliency framework would be aligned to the development of 2D saliency model, which has a more fast-paced perspective than the development of 360 saliency model. Thank you very much for your attention. Please, if you have any question, contact me via email.